Here's an example of using trigonometric substitution to solve an integral. This is a technique that's good for solving integrals of certain kinds of algebraic functions that include an expression like this, the square root of 1 minus x squared, as part of the integral. Algebraic functions involving radicals like this that can't really be simplified can be very difficult to integrate unless you get lucky and come up with a very clever choice of a u substitution to make it work. And sometimes that just won't work at all. What we can do in this situation is introduce some trig functions that, believe it or not, will actually help make our lives easier because they will allow us to use various trigonometric identities that we're familiar with to simplify the integrand and be able to solve the integral. To figure out what to do here, it makes sense to first think about a related integral, the integral of just 1 over the square root of 1 minus x squared dx, just like this. This is an integral that would be very difficult to figure out if you didn't already know the answer, but we do know the answer because we recognize that the integrand is actually just the derivative of an inverse trig function. In fact, it's already the derivative of the inverse sine function, arc sine of x, or sine to the minus 1 of x. Remember, that minus 1 there is not an exponent. It just indicates this is the inverse function. I prefer to write arc sine of x, and of course you have to add a c here. Since we already know that the derivative of arc sine of x is 1 over the square root of 1 minus x squared, we solved that back in calculus 1 using implicit differentiation. Since we know that already, we know therefore the antiderivative of that expression is arc sine of x, inverse sine. The integral we're actually trying to solve is pretty similar to this, except that it involves an x cubed on the top. However, this integral of inverse sine that we know gives us a bit of a hint as to what to do to solve this. Here's what we're going to do. Let's start by making a substitution. Let's decide to set x equal to a trig function. Let's let x be the sine of some new variable. Traditionally, we change the variable to theta. Now, in u substitution, you are using a method of changing the variable in a way that you hope will simplify your integrand. In this situation, we're going to also change the variable, but notice that this time, instead of replacing a function of x with a new variable u, we're replacing just the variable x with a function of theta. But otherwise, substitution works in a very similar way. We still need to take the derivative of this expression. The derivative of x is dx, and that equals the derivative of sine theta, which is cosine of theta, times d theta. At this point, we can actually substitute everything into the integrand. The substitution step here is actually much easier than it is with u substitution, because you can just replace the variable x with this function. The catch there is that you might end up with a very complicated looking integral. But let's try it. This integral equals the integral of, well, x cubed. X is sine theta, so I can say sine cubed theta. Now dx is equal to cosine theta d theta, so I'll put that there, cosine theta d theta. And we are dividing by the square root of 1 minus x squared, but x is sine theta, so we'll put sine squared theta in here. We now have a brand new integral that is entirely in terms of this new variable theta. And we're ready to use whatever tools and techniques we can think of to solve this. Now you might look at this and think, well, this is a much more complicated and nastier looking integral than we started with. But here's the trick. Let's go back and look at the same trigonometric identities that we made use of in the last section on trig integrals. In particular, let's look at the Pythagorean identities. Remember our basic Pythagorean identity that sine squared theta plus cosine squared theta equals 1. This is true for all possible values of theta. let's make use of that to see if we can simplify our integrand in our integral. So we know that sine squared theta plus cosine squared theta equals 1. But that means that cosine squared theta equals 1 minus sine squared theta. So I can actually replace the expression inside my square root with cosine squared theta. This whole integral equals the integral of sine cubed theta times cosine theta d theta over the square root of, well, 1 minus sine squared theta is just equal to cosine squared theta, so I can write cosine squared theta under that square root. But the square root of cosine squared theta, that's just cosine of theta. And furthermore, now we're just multiplying on the top by cosine theta and then dividing by cosine theta. So we can actually cancel these guys out entirely. Our integral is actually equal to just the integral of sine cubed theta d theta. So now we just need to be able to solve the integral of sine cubed theta d theta. This is not too hard to do. This is an integral very similar to ones we've solved in the last section on trigonometric integrals. We know that we can just split off one of those sine thetas to be part of a du and do a u substitution. This is equal to the integral of sine squared theta times sine theta d theta. And now let's do a u substitution. So we've already done one substitution. We let x equal a trig function of theta. Now we're going to do a u substitution. We're going to let our u equal a function of our existing variable. And we want our du then to be the derivative of that function. Now, we see that we have a sine theta d theta sticking out here, so let's let our du be something related to sine theta d theta. But our u, therefore, has to be the function whose derivative is our du. So the u function is going to have to be cosine theta, which means that our du is actually the derivative is going to be negative sine theta d theta. Now, you could have set your u to be negative cosine theta if you wanted to, and that would mean that your du is positive sine theta d theta. But it's usually easier to keep the u as simple as possible, and if there are any negative signs to be dealt with, stick them on the du instead. So, as usual for our trigonometric integrals, we have a bit of a problem here, that the rest of our integrand that isn't part of du is involving sine theta instead of cosine theta, where our u is cosine theta. But that's okay. We can use the Pythagorean identity again to simplify that. Again, let's recall that sine squared theta plus cosine squared theta equals 1. That means that sine squared theta is actually equal to 1 minus cosine squared theta. This equals the integral of 1 minus cosine squared theta times sine theta d theta. And now we're ready to do our u substitution to fill in the u here. This integral equals the integral of 1 minus u squared times negative du. I'm going to put the negative out front here in front of the integral and put our du here because our du is negative sine theta d theta, but I only see sine theta d theta showing up in my integral. So I've just made some more room here by erasing some of the steps we've done to get to this point. But I want you to notice we have done two different substitutions here. First, we replaced the variable x with the trig function sine theta. Then we replaced the trig function cosine theta with u to do a traditional u substitution. That means that after we finish finding our antiderivative, we're going to have to do two substitutions back. So let's just keep that in mind. That's why I've saved my x equals sine theta and u equals cosine theta so that we can see that and we'll be able to use that at the end of this. Before we do that, though, we still need to finish our integral. We have not yet found the antiderivative of the function here. What I'd like to do first, though, just to keep things organized, is let's just multiply that negative sign right back in. The integral of 1 minus u squared the negative of the integral of 1 minus u squared du is actually going to be u squared minus 1, the integral of that times du. And this is an easy integral to solve. This is just going to be 1/3 u cubed minus u, and plus a constant, of course. Very important that you do keep track of your variable here. The integral, as we last looked at it, was entirely in terms of the variable u, which means that when we do the antiderivative, everything should be in terms of u. U is the only variable that exists here. Now we're ready, though, to substitute our other variables back in. So let's start by bringing this right back around here. And what we have is 1/3 of u cubed. Well, our u is cosine theta, so u cubed is cosine cubed of theta. And then minus u, so that's minus cosine of theta, plus constant. But our original integral was in terms of x, so we shouldn't have an answer that's in terms of theta here. We need to figure out how to convert our cosine of theta back to be in terms of x. Let's take that on a separate page. So originally, we decided to let x equal sine of theta. But now our answer is in terms of cosine theta, and we need to convert that. There's a few options here. One option is you could say, well, the inverse sine of x is theta. All you're doing here is solving the first equation for theta. So that means that we could take the cosine of theta, and that is just the cosine of the inverse sine of x. This is technically a correct answer, but it's a very, very nasty answer. Any time that we ever find ourselves plugging an inverse trig function into a trig function, or vice versa, we should stop, get rid of this, because there is always a simpler and neater way to write this. In fact, there's always a way to do it in an algebraic way. So we don't want to do this at all. Sometimes you'll have to do this first part of solving for the variable theta. But you do not want to then take a trig function of that variable and end up with a trig function of an inverse trig function. Instead, let's draw a right triangle. Let's put it right here. It is pretty traditional to have the right angle at the bottom right, but it doesn't actually matter where you put it. And it's traditional to put our angle theta. Remember, theta is an angle, that's why we're taking a trig function of it. Put that angle theta at the bottom left. Now, x is sine theta. Sometimes it's useful to use a unit circle when handling trig functions. Other times it's useful to use a right triangle. This time the right triangle is the advantage here, and our trig function sine theta is equal to a ratio of 2 of the sides of the triangle. And let's actually say, since that's equal to x, let's just write it as x over 1. Now, which 2 sides is sine the ratio of? Well, sine is the opposite side over the hypotenuse. This is by definition, right? So we could choose to label our triangle and label the opposite side opposite the angle, as x, and label the hypotenuse as 1. Now, if we do that, let's work out what our third side is. We can use the Pythagorean theorem. Question mark squared plus x squared equals 1. If we solve for question mark, here's question mark squared, that equals 1 minus x squared, which means that our question mark is equal to the square root of 1 minus x squared. So we can get rid of this question mark here and call this the square root of 1 minus x squared. Does that look familiar? That's the same radical that appeared in our integral to begin with. And the only way that you can get that exact radical to show up in this right triangle is if you make the choice to substitute sine theta for x. If you have a different form of radical showing up in your integral, you'll want to use a different trig function, which will change the configuration of where the various labels are on this right triangle, and you'll end up with a different root. If you've done it right, though, the same root that appears in your integral will appear on this right triangle. So now that we've labeled all three sides of our right triangle, it's easy to find any trig function we want to, because every trig function is just a ratio of two of the sides of the triangle. So back to our question, what is cosine theta? Well, cosine theta, by definition, is the adjacent side over the hypotenuse, the side of the triangle adjacent to the angle. That is the square root of 1 minus x squared. That's what it's labeled as, divided by the hypotenuse, which is 1. So that means that actually cosine theta is the square root of 1 minus x squared. And guess what? We already knew that, because when we actually were setting up our integral and doing that first substitution, we found that once we plugged sine theta in for x in that radical and did all the work to simplify it, we found that it actually simplified down to cosine theta. That's why we made this substitution in the first place, was to cause that radical to simplify and go away. So the same thought process is going to show up multiple times in these problems. Don't forget that you've done it the first time. Keep track of the work you've already done and go back and look and see what answers you already have as you're solving these problems. So now let's go back and finish solving our integral. So we determined that cosine of theta is the square root of 1 minus x squared. Now we have a cosine cubed here, so we'll have to cube this expression. And we have 1/3 of that, minus cosine theta, which is the square root of 1 minus x squared, and plus a constant, of course. Now, we could just put a box around this answer right here. It's perfectly fine. But since I noticed that I'm taking a root of this expression and then cubing it, that's really 2 powers. So maybe I'd like to just simplify that power a little bit. So I've got 1/3 times 1 minus x squared. Now, I'm cubing that, but I'm also taking the square root. It doesn't actually matter which order you're doing that. The square root is actually the 1/2 power. So really, if I'm taking the 1/2 power and then cubing that, I'm taking the 3/2 power. And then minus, I could write 1 minus x squared to the 1/2 power, or I could write it as the square root. Maybe I'll just write it as the square root like I had before. 1 minus x squared, square root of that, plus a constant. And this is probably the nicest, most simplified form of our answer. Like I said in a previous section, the answers to these integrals are often going to be kind of ugly, nasty, complicated functions. That's okay. That's normal in calculus. That happens sometimes. So don't think that just because your answer is pretty complicated, that it's wrong. But the disadvantage here is that sometimes your answer may look different than somebody else's answer, but they may both be correct because you may have 2 different answers that are algebraically equivalent. So be careful about that. This is going to really test your skills of algebra.